Welcome back, everybody. We're going to be starting, or going to be finishing up 1.4 today, hypothetically starting 1.5. Students asked to maybe do a little bit more on dimensional analysis or unit conversions. So if we have a little bit of time at the end, we will do that. So we left off last time talking about adjacent versus opposite sides and trying to identify the adjacent opposite side in relation to the angle in question. So for example, angle A, its opposite side, if you draw a line straight out from it, this is the opposite side, whereas the adjacent side is the side that is touching, and the hypotenuse is always the hypotenuse, because yes, technically speaking, the hypotenuse is an adjacent side to A, but it's more in particular, it's more concretely, it's the hypotenuse. So we didn't get to start with the trig ratios. We didn't get to finish it, so let's go ahead and finish it. So we have three main trig ratios. The first one is sine, spelled S-I-N-E, of angle A or B. And it's denoted S-I-N. So that we don't have, like, I don't know why, we're just trying to save on time so we don't write the E. I guess that's the main reason, just saving us one letter at a time. So sine parentheses A. And so that's not sine times A. I think we talked about this a little bit, maybe not. No, we hadn't. That is not sine times the quantity A, that is sine of the quantity A. Sine is like an operation that is performed on something. So it's saying sine of this quantity. So you can think of sine of like a grouping symbol, like parentheses or brackets or things like that, or absolute values. And sine is opposite divided by hypotenuse. In relation to a triangle. So it's the opposite side over the hypotenuse. The secondary trig function is cosine. So it's the exact same spelling, except there's a co in front, C-O, not K-O, C-O. Cosine of angle A or B. I'm just writing the A or B just purely to mention that this could be true. Like this works for both angle A and B. It doesn't matter which one. And we abbreviate cosine instead of SI, like we don't do COSIN, we do COS, and that's just cuz. Haha, hilarious. Trig has so many funny jokes. Cosine, and that's going to be adjacent over hypotenuse. And last one, I hope you'll excuse me, guys. I need to go off on a tangent. Hilarious. So, tangent is the last of the three main trig functions or trig ratios. Tangent of angle A or B is written TAN, so just tan, the first three letters of A, and that's going to be opposite over adjacent. Now, there are three other trig functions that are just the flipped versions of them. So there's a thing called cosecant, and cosecant is just hypotenuse over opposite. So it's just taking this function and just flipping it on its head. There is secant, which is taking hypotenuse over adjacent, so it just flips cosine. And then there is cotangent, which just flips tangent. So instead of opposite over adjacent, it's adjacent over opposite. However, those ones are more useful for Math 127, which is pre-calculus 2, trigonometry. We're going to study just the pure basics here. But there are other ones. And just as a fun little observation, because I wanted to tell you this joke. So if you notice, if you take sine, you don't need to write this down, by the way. This is just for sillies. Cosine of A over sine of A over cosine of A. That'll be opposite over hypotenuse divided by adjacent over hypotenuse. And if you remember about fractions, when you divide by a fraction, you flip and multiply. So this is opposite over hypotenuse times hypotenuse over adjacent. The hypotenuses cancel, and you've got opposite over adjacent, which is tangent of A. So the joke goes, why do mathematicians never need to go to the beach? Because all they need is a sine and a cosine to get a tan. Haha, haha. That one's a much cornier joke, in my opinion. So we'll take, so here's the thing. We'll take this as a sign from above. Badunks, another one, another joke. Okay, to move on. As a small warning, I guess I'll just say small warning. Since the adjacent and opposite sides depend upon the angle, sine sine of A doesn't equal sine of B necessarily. Same for cosine and tangent. So what I'm trying to say here is that sine of A is not equal to sine of B. There is one situation where that will be true when you have a 45-degree, like a right triangle with two 45-degree angles, at which point A and B are the same. But that is the only case where that happens. Sine of A is not equal to sine of B in general. So just because you found sine of A does not mean you know what sine of B is, just so we're clear. Now, that's a lot of things to memorize. Sine equals opposite of hypotenuse, cosine equals adjacent over hypotenuse, tangent is opposite of adjacent. That's a lot of things to memorize. And then for whatever reason, this is the remembering trick. You might have heard it before. Miss Arrington told it to me way too many times when I was taking trig, and that was SOHCAHTOA. Johnson just reminds me of that that episode where they get the superpowers in SpongeBob and he says Krakatoa, whatever. That's all I can think of when I hear SOHCAHTOA. But SOHCAHTOA is the trick to remembering it. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So that's the remembering trick. And most people, I like it. Trig's been out there for hundreds of years, and we still can't find a cool way to memorize it just besides just saying SOHCAHTOA and say accept it. I haven't thought of one. If you can think of a better one, maybe we can make it we can make it a thing. We can make it a cool thing to do. But until then, just SOHCAHTOA. So, KAHTOA. As an example, find the trig ratios for A and B below reduce fractions as much as possible. Did you need anything? Okay. So it gives us a triangle in this picture, in this problem. Not drawn to scale, of course, but it labels it top left is A, bottom right is B, bottom left is C, which is where the right angle is. And then it tells us what that the hypotenuse is 75 meters, the base leg is 72 meters, and then the height leg is 21 meters. So we'll find we'll find the trig ratios for A first and then B, but then again, it doesn't really matter if you want to go backwards and forwards and stuff. You can do that. You can find sine of A and sine of B, cosine of A, cosine B, tangent A, tangent B, however you want to do it. Doesn't really matter to me. So let's just work with for A. Oh, wrong color. For A. Sine of A is, once again, that's opposite over hypotenuse in relation to A. So the opposite side for A is the 72, exactly right. If I was to draw a ray stemming out from A, angle A, the first thing I would touch would be that the side length CB. So opposite side is 72. Hypotenuse is always the hypotenuse, which is 75. Notice I said reduce the fraction as much as possible. So what that means is we're going to try and find common factors. And it just so happens that each of these things is divisible at least by 3. And the good news is if you bought the calculator I suggested, it will reduce the fraction for you. So that's a nice nifty thing about it. But otherwise, you can still just realize that 72 is 3 times 24 and 75 is 3 times 25. So this actually reduces down to 24 over 25. And that's as far as we can go because 24 and 25 are what we call relatively prime, which means they have no common factors. That is sine of A. Cosine of A is, once again, that's adjacent over hypotenuse. So the adjacent side then must be the 21. That is the side that A is touching, that is not the hypotenuse. So that's going to be 21 over 75. And just like before, there's a common factor of 3. Because 21 is 3 times 7, and 75 is 3 times 25. So this reduces down to 7/25. And as a fun little thing to ponder, just in case you haven't heard it before, you probably heard it growing up as a nifty little fun thing about divisibility of numbers. But every number that's divisible by 3, its digits add up to 3. Or sorry, digits add up to a number that's divisible by 3. So 7 plus 2 is 9. 7 plus 5 is 12. Both of those things are divisible by 3. 2 plus 1, that's 3. That's divisible by 3. So on and so forth. Just a nifty little thing. It's a fun little observation. And if you're curious, like number theory has to prove that, but I digress. Last one, tangent of A. That's going to be opposite over adjacent, SOHCAHTOA. So opposite side for A is 72. Divided by adjacent side, which is 21. Once again, they have a common factor of 3. This is actually equal to 24 over 7. Now you maybe think, oh yes, go ahead.
I'm sorry, maybe you might have already mentioned this. So since it's A, like next to say cause, would we like start with A? Would that be like where we
Yes, that's where like that is the angle that we're going to be using.
is it always gonna be or is it gonna be different?
So like if I'm saying angle A, then we're going to identify angle A and utilize that one. Yeah. But if I say find sine of B, then we'd have to use B as our reference angle. So we've already written the SOHCAHTOA. So I'm just going to write for angle B. And I'm just going to write sine of B. I'm not going to write O over H anymore. Cosine of B equals, and tangent of B is equal to. So for B, then the opposite side, if you draw a ray out from B, will be the 21. So the side opposite to B is 21. The side adjacent to B that's not the hypotenuse is 72. So we'll utilize those in here. So sine is SOHCAHTOA, so opposite of over hypotenuse. So that'll be 21 over 75, which we already found out reduces to 7/25. Cosine of B will be the adjacent side to B, which is 72, divided by the hypotenuse, which is 75, which we already reduced down in the previous problem to 24 over 25. And then tangent of B is opposite over adjacent with respect to B, that is. So that's going to be 21 over 72, which reduces down to 7/24. So just as a small little thing to observe here, notice that sine of A and cosine of B give you the same number. And cosine of A gives you the same number as sine of B. And then tangent is the whole thing. That's the reason why we call them, why it's called cosine. We call them, later on in your mathematical career, you call them cofunctions because they are kind of two sides of the same coin. They both are very, very closely related to each other. There's a lot of really good beauty in trigonometry. Does anybody have any questions on that? Okay. One thing that I want us to all do on our calculators, because for this class, so in some classes you switch between the two of them. Sometimes you stick with radians, but we are going to stick with degree measurements. So you need to make sure that your calculator's in degrees. If you're using a Casio, there should be a highlighted button at the top that either says R or D. If you have a button that's highlighted and saying R, that means you're in radians. And you need to change it to degrees. One of the, like, if you've got the other one, you'll need to mess around with it. But if you want to change it, go to Shift Setup. So press the Shift button, and then right next to menu, there's Setup, and then go to Angle Unit, and then it'll give you either degree, radian, or gradient. We're going to do radians. So, or sorry, degrees. So press 1. If you need help changing yours, please let me know, and I'm happy to change it after class or whatever. But for this class, we are going to always be using degrees. If you're wondering what a radian is, by the way, if you're curious about it, because it is kind of a weird word, it's and you don't need to draw, you don't need to write this down, but this is just for informational purposes. If you were to draw a unit circle, or well, just any circle with radius, say R. If I were to take this distance, that distance R, and basically cut it, like cut a piece of string that was that big, and just strap that piece of string. Let me just try and grab it quick. So if I were to take this piece of string, and kind of wrap it onto here, so it would eventually look like this, the angle that's formed by that is 1 radian. The angle that's formed by that is 1 radian. And you'll find out that you have 2 pi radians in a full circle, which is fascinating. But that's how a radian is formed. That's what a radian is. But we're going to use the more real life measurements, which is degrees, which comes from the Babylonians, actually, fun fact. Because they worked in, I think we talked about this a while back, but they worked in a base 60 system, and that's why there's 360 degrees in a full revolution. That's kind of an old, that's a remnant of the past. But so there's 360 degrees in a full circle, and that comes from the Babylonians. But anyways, the reason why I want us to convert our calculators to degrees is because sometimes in your homework, you're going to need to compute them. So compute with a calculator and round to tenths, hundredths, 10,000ths. Which is 4 decimals. And we're just going to do these right off the bat. So A is going to be sine of 38 degrees. And B is going to be cosine of 33 degrees. If your calculator is in radians, you will get a completely different answer. Because 38 radians is a lot different of an angle than 38 degrees. 38 radians is like several revolutions, or like several 360-degree revolutions. But either way, so sine of 38 degrees, if I plug that into my calculator, because one of the things here, there are very few angles in mathematics that have rational answers, meaning like fractional answers, like 1/2 or 1/4 or whatever. There are very few of them, and most angles, when you plug them into a sine or a cosine, will give you an irrational number. So there's no way to compute it by hand. But so sine of 38 degrees is roughly 0.61566 ... on forever, because it's an irrational number. And since we're going to be rounding to the nearest fourth decimal, so looking at that, that's a 6. The digit to the right of it is also a 6. So we will round up to 0.6157. Back in the day, though, when calculators weren't a thing, so there is a way to approximate it. There is a way to approximate sine and cosine and tangent to a reasonable degree of certainty. And like we used calculators to do it, but most people didn't have, like, I mean, unless you wanted to bust out one of those giant calculators, right, that has like the roll of parchment and makes the sound, then you wouldn't be able to bring that to school. And so what they did is in old textbooks, they actually had a chart that had like basically sine of 1, sine of 2, sine of 3, sine of 4, sine of 5, all the way up to like 180 degrees. And so you had like, if you needed to do a problem that involved trig functions, you had to like look at the glossary to find those values, which is a pain and a half. It's a little bit before my time, but still.
I'm sorry, so to find this, you just put sine and then.
Yep. So, I should have told you about that. So all of the scientific calculators should have a trig the trig functions, specifically those 3. They don't have a cosecant, cotangent, and secant button, but all you need to do is just press sine. It should show up on your calculator saying sin or cos or tan, and then go from there. So if you're not getting that number, by the way, it's probably that you're in radians and you just need to switch it, but you can always come talk to me after class and I'm happy to fix it in case you can't find it yourself. Cosine of 33 degrees, that is approximately, so it's the decimal expansion for as long as we can get it. It's going to be 0.838670 on and on forever, which we're going to round to 0.8387. So we're rounding to the nearest 10,000ths. Oh, I forgot to do 2 more of them. C will be sine of 135 degrees. Now your calculator might say square root 2/2. Just press the S to D button to get the approximation. That's going to be one of the special angles that actually gives you a finite number that's easy to write down. But we want it as 0.70710 on forever, which approximates to 0.7071. You're going to round down. And let's just do one more for good measure. Let's do a tangent one since we've done one of sine and two of sine and one of cosine. So part D, tangent of 17 degrees. I should have been writing the degree symbol, but I didn't. And if you plug tangent of 17 degrees, you should get 0.30573 forever, which is approximately 0.3057 when you round down. Now, this is all fine and dandy, right? This is all fine and dandy, but how the heck do we utilize this? How is trig going to be useful for us? And we're going to do a math example for, oh, yes.
So
Say again. Oh, why would I not put degrees at the end? Excellent question. Excellent question. Why is it no longer degrees? And that is a great question. So sine function, or like trigonometric functions, they take in an angle and spit out a ratio. So yes, we've written these as decimals, but technically speaking, they are ratios. And so it takes in an angle and spits out a number. That's how so it is what we call a function. And functions, what they do is they take in an input and spit out a new output. And in particular, with trig functions, they take in an angle and spit out a number. So that's why it doesn't have any measurements at all, because it's just a ratio. Yeah. Excellent question. Nobody's asked that before. And I'm glad I got to explain that. Yes. Any other questions? Okay. So how do we utilize it for things like this? Example. So we're going to look at a pure math example, and then we're going to look at a quote unquote real life example. So the first example is find the measure of side lowercase b when you're given this triangle. This right triangle, we should say. So A is in the top right, B is in the bottom left, C is in the bottom right. And then it shows you that the angle B is a 32 degree angle. And you've got the base side length here of 22, but that's it. And fun fact, you can find everything there. You can find all the bits and pieces of the triangle just with that, which is pretty cool. So we want to know the side measurement of B. So B is the side that's opposite of angle B. And then we can just label the hypotenuse, but we're not interested in the hypotenuse. The problem doesn't ask us to find it. So we don't need to worry about that. We just need to worry about angle B, or sorry, side length B. So solution. You've got sine, or sorry, for angle B. For angle B. Now, when you get better at this, when you start doing this for as long as I have, I don't need to write this stuff. And if you feel comfortable identifying your adjacent, your opposite, and your hypotenuse sides by yourself in your head, be more power to you. In fact, I'd encourage that. It saves you some carpal, it lowers your risk of carpal tunnel syndrome, since you don't have to rewrite it every time. And it also works on your mental math. So if you don't want to write this down, you don't have to, but I'm going to identify them for now. The adjacent side, the ADJ, is 22. The opposite side is B, and the hypotenuse is C. Now, the reason why this is important is that since we now know that we can plug in, like our calculator can calculate angles, trigonometric functions of angles, it can find sine of 32. can find cosine of 32 degrees, and it can sine tangent of 32 degrees, we can utilize that to our advantage. So we just need to figure out which trig function to use. So, and the good news is, by the way, you've only got 3 choices. You got a 1 in 3 chance of getting it right on your first go, like if you're guessing, and you can keep trying it out. What's the worst thing that happens if you set up the wrong trig ratio? You just have to erase it. It's not a big deal. So I'm just going to write SOHCAHTOA for my brain for a second and say, which trig function would I need to use? So I want b, lowercase b, and that is the opposite side of b, right? So cosine is out of the question because cosine doesn't relate opposite to anything. Should we do sine then or tangent? Let's try sine and see what happens. Worst thing that happens, I'll tell you it's not going to be right, so you don't have to write it down, but I want to show you how I would work through it. So I'd start off, okay, well, sine's got opposite in it, so I'll do sine of 32 degrees. That's going to be opposite b over hypotenuse c. Oh, that's 2 unknowns because sine of 32 degrees, that's a known value. It's going to be an approximation, but it's a known value. But b and c are unknown, and I can't solve 2 variables at the same time unless I have multiple equations, but that's something for a later course. So this doesn't work. So sine is out as well. That one's out as well. You also know that it's out because we have we want to know the opposite side length, and we have the adjacent. So that means that tangent is the best choice. It's the only choice, really. So that'll be what we use. So tangent of 32 degrees is equal to opposite over adjacent, which in this case would be b over 22. Any questions so far? So to make it look less muddy, I'm going to get rid of the O over A. I'm just going to write tangent of 32 degrees. And by the way, you don't have to write the 32 if it's assumed from the context, as mathematicians love to say. You don't have to rewrite the degree measurement. It's encouraged, but it's not required. Most of the time, we typically skip it in upper division mathematics. But either way, the point being is that I'm not going to mark you down if you don't write a degree measurement there. That's not like degree measurement when you're finding an angle, yes, but when you're utilizing it in an equation, go with it. So this is a weirder situation that we haven't encountered yet, because how do I solve for b? Now, the most exact way to do it is to remember that sine, here's a way to think about it. How would you solve this? Don't write this down, but how would you solve that? There are 2 main ways. You would either, what do you think?
Multiply by or
Multiply by 22 would be one option, or you could treat this as a fraction and cross multiply. Either way is fine with me. Either way works. And so I give this specific simpler example to remind us tangent of 32 degrees is just a number. It's an irrational number. It's going to be a decimal approximation, but it's just a number. So it gets solved the exact same way as you would if you had 2 equals b over 22. So you're going to take this equation and multiply both sides by 22. And get that b is equal to 22 tangent of 32 degrees. And I know that looks weird, but remember, tangent of 32 degrees is just a number. So really all I'm doing is I'm taking 22 and I'm multiplying it by like 0.6-ish. right? 32 degrees, that's a little bit more than 30. Yeah, about 0.6. So then I just need to plug this into my calculator. That's going to be 22 times tangent of 32 degrees. And you should get that B is approximately 13.7, or let's just round to 2 decimal places, 13.75. And since units were not specified, we don't need to write units. If units aren't specified, we can skip the units. Yes.
So this problem is basically like both of the other problems together.
It's utilizing, now that we know how to utilize trigonometry, now we know how to set up the ratios and how to plug in the values into the trig functions. Now we can utilize those to find different angles. Now notice, we could also find C. We're not tasked with finding C, but we could, which trig function would you use to find C? Take a second, don't answer it. Sorry, I should have specified. Take a second to think about it. Let everyone get a chance to think. I think I heard someone say cosine. And yes, cosine would be what you'd use to find angle C, because that's, you have the adjacent side and you need the hypotenuse. The only one that relates to adjacent and hypotenuse is cosine, and that's the one you use. So I would honestly recommend, by the way, this is an easy way to memorize sine, cosine, and tangent, and to get practice with how to set this up. Always write SOHCAHTOA and try and identify which trig function you need based on your situation. And you can just work through process of elimination. As you get better and better at this stuff, you don't need to, but that's just free memorization. That's just free memorization. Any other questions? Now, oh yes, go ahead.
You had 2 side lengths written down that were given to you
Mhm.
so if you had the opposite and the adjacent, trying to find the hypotenuse, would it matter which one you did to solve it?
Excellent question. So if you were given, let's just say they actually told you that this was 13.75 and they wanted you to find C. Now you could use either trig function to do it, but there's actually another way you could do it. The Pythagorean theorem. So if you're given 2 side lengths of a right triangle, you can find the third by the Pythagorean theorem. But yes, you can use either. You could use, if you're given both of these and you want to find C, you could use sine, which is opposite over hypotenuse, or you could use cosine, which is adjacent over hypotenuse. And both will get you the same answer. Great. Great question. Any other ones? If writing it as tangent of 32 degrees is freaking you out a little bit, you can always write down the approximation of that number first. So I'll say alternative. If you don't like writing tangent of 32 degrees a lot. So if that's freaking you out a little bit, you can just calculate it off the hand. So you've got tangent of 32 degrees is equal to B over 22. And then if you plug tangent of 32 degrees into your calculator, you get 0.62486935919. Yes, I'm going to write out every digit that I can. So 62486935919. The reason I'm going to write down every decimal that I can see is because this is an approximation. If I just wrote 0.6, the answer that I get will not be the right answer. I mean, on an exam, I probably would give you full credit because you're doing everything that I need you to do. But on Canvas, it's using the exact value of tangent of 32 degrees to calculate this. So by writing as many decimals as you can, you will limit the amount of error that you have in your answer. You had a question.
Would that be even if, like, for example, it was 0.6242424? Or would you want us to just stop it at 24? Like if it's
if it's a repeating,
yeah.
It never will be actually. With like, excellent question, but it will never be that for trig functions because I mean, there may be a very, very strange case where that happens, but it's very few and far between. I'd be shocked if we actually get that. So yeah, the chances of that happening would be non-existent. But yes, if it did write 2-4, 2-4, 2-4 and repeated, then you could just stop at 2-4. So, but if you want to do it this method, then you've got it, and now it looks a little bit more relatable because it's just a number equals b over 22, but you still solve it the same way. You'd multiply both sides by 22, and you'd get the same thing. You'd get b is equal to 13.75. So it's just your prerogative. It's whichever one you want to do. I like using the tangent of 32 because I think it gives us a little bit better understanding of our number sense, and realizing the tangent of 32 degrees is just a number, which can help you later on in your mathematical career. But if you're not vibing with that, you can definitely write it as a decimal approximation. So let's go ahead and now look at an example, like a specific word problem example of how you can utilize this. Example: a plane takes off from the ground at a 14-degree angle. After flying straight for 15,000 miles. No, that can't be right. 15,000 miles would be massive, right? Like how big is, like how tall is the, what's the height of the atmosphere? Let me know. What's the height of the atmosphere? Okay, the atmosphere extends to 12 kilometers, so 15,000 miles would be insane. Let's go ahead and do 15,000 feet. 15,000 feet. We're not going into space. After flying straight for 15,000 feet, what is the altitude of the plane? That's terrible handwriting right there. Altitude. What is the altitude of the plane? And we'll round to the whole number. Round whole number. So whenever you're given these situations, sometimes you're given a picture, in which case kudos, yay, but otherwise you need to draw your own picture. Mathematicians are the ones that coin that phrase that a picture is worth 1,000 words, because it really helps you figure out your math problems. It might seem stupid, but a picture can really, really help you jog your memory of different quality, like quantity, like properties that you know about triangles. So we got this super cool airplane with a rocket booster. Very important. He's saying woohoo. And then, so this guy or girl or them, whatever they may be, they are going at an angle of 14 degrees. So this is 14 degrees. And it says they're flying straight for 15,000 feet. So that's not the height. That is the hypotenuse, is 15,000. Which is kind of the hard verbiage. And with this problem, because because I'm doing the problem in front of us, that's why I'm going to say that that's that. I would make sure to be very, very clear on an exam, unless it was very, very clear from the context. But this one is straight, makes you think that it might be talking about the linear distance, but the bottom is the linear distance. We're talking about the distance that they're flying up. And then we want to know the altitude. And I didn't draw this as a perfect right triangle, but just ignore that. And so the altitude is this. We'll call it X, and that's the thing we don't know. So we need to use trig. We need to use trig. So I'll rewrite it again. But as you go through this, you start to not need to write this as you get better and better at it. So we have the hypotenuse. That's one of the given side lengths. So we know tangent's already out. We don't need tangent because we have the hypotenuse and we need to find the side opposite of the 14-degree angle, which means we're going to be using sine. The sine is opposite over hypotenuse. So sine of the 14-degree angle is equal to opposite, which is X, over hypotenuse, which is 15,000. At which point, we can now solve this however you want to. And I'm just going to multiply. I'm going to do it the way that I like to, but if you want to, remember, you can always write sine of 14 degrees as a decimal approximation first, but I'm going to multiply both sides by 15,000. Canceling it on the right and getting that X is equal to 15,000 sine of 14 degrees, which is approximately, when I round to the nearest whole number, 15,000 times sine of 14 degrees is 3,629 feet. And yes, this is a completely fabricated example and like not really something that you'd be able to do with your naked eye, but our instruments, like for a like, have you ever wondered how they calculate altitude and things like that? Sometimes these types of these calculations are what the computers are doing, not necessarily this one, but these are the types of things that are happening inside those systems to figure out altitude or like all those things that we rely on. So anyways, any questions on that? One last thing, we'll still be doing more trig stuff, but one thing I need to mention before we go on is a little subsection called the angle of elevation. / depression. Not as in like the clinical depression, but as in like the most literal sense of the word depression, meaning like to depress something, to push it down. So this is something you will see sometimes mentioned in some of our problems in our homework and or on our exams, and then in real life. So what is the angle of elevation? So AO, which I'm going to write as AOE or AOD, angle of elevation or angle of depression. So the AOE, the angle of elevation, when you're doing that, you have to, like it's always based on an observer. So the observer is right here. Not like a StarCraft observer for any of my people. I mean, is StarCraft still relevant? Has anybody played? No, I figured not. That's a while back. But anyways, if you were to draw a straight line out from the observer, and then let's say your object being observed is up here. Object being observed. Then, if you form an angle like that, that is the angle of elevation. It is based on the observer's perspective how many degrees they would need to look up to see the object in question. So this is the angle of elevation. That's how we define angle of elevation. It is how much the observer needs to raise their head or whatever to see, like wherever the observer's frontal view is, how long they would need to change. In stark contrast, or in like similarly, the angle of depression, so the AOD, still, once again, from the observer's perspective, and just standing there and we draw a straight dashed line out. That would be their field of view if they were just looking straight out ahead. And then down here is the object being observed. And so the angle being formed, this is the angle of depression. Point being is that once again, that it's just from the observer's perspective, how far they are looking up or looking down. Like if you were to put their head perfectly on a protractor and follow their eyes, how many degrees would they go up or down? That's the angle of the elevation or depression. So as an example of this, a security light is going to be mounted so that the angle, the AOD, the angle of depression, is 30 degrees. How high up should the light be, like, how high up should the light be placed? Or how high up should the light be so that it will shine on a spot that is 20 feet from the base of the building? Now, how high up should it be placed so that it can shine in a spot that's 30 degrees from, or sorry, 20 feet from the base of the building? And this one's kind of hard to grasp while you write. Don't worry, I'm not going to start the problem for a second because I know I write that quickly. But I deliberately choose to do these problems because they're very tricky. No, that like, but in all seriousness, they are deceiving for one specific reason. So, draw a picture. You'll see what I mean in just a moment. So here's our building. You know what? They've actually got one of those cool archways. Building. All right. And then you're placing this security light right here. You don't know how high up it's going to be. You're going to keep, like, I mean, the more realistic thing that you would do is you just keep messing with it until you got what you wanted, right? You wouldn't actually sit there and mess around with it perfectly. But, well, actually, no, because you're trying to place it here, since you're trying to place it, you don't want to re-drill into the wall several times. So it says that the angle of depression, so from the observer's perspective, from the security light's perspective, the angle this angle needs to be 30 degrees. And we want it to shine on a spot that is 20 feet from the base of the building. And we don't know X. All right. So here's the thing. Don't write this down. John Doe student, silly John Doe. John Doe's getting started. And he says, oh, this is easy. I got this. That gives me the adjacent, that gives me the opposite side, and I need to find the adjacent. That's tangent. So I'll just go tangent of 30 degrees is equal to 20 over X, adjacent over opposite. Done. Or sorry, opposite over adjacent, excuse me. Why is John Doe student wrong? What's wrong here? Yes.
That's not the degrees of that.
Exactly right. That is the degree angle measurement of this triangle up here. That's a different triangle. Now, granted, there are two parts of the same rectangle. So technically speaking, if you really want to, you can use the 30-degree angle and just realize that this should be 20 and this should stay X. But either way is fine. I'm going to do it a different way, but that is one way to do it. The way I would like to do it is to say that we can find this degree measurement. This is forming a right angle. And so that means that this whole thing should be 90 degrees. So green angle plus 30 degrees has to equal 90. The green angle plus 30 degrees should equal the whole 90 degrees. So we'll subtract 30 degrees and get that the green angle equals 60 degrees. And now, so the correct then is not tangent of 30, it's tangent of 60 is equal to 20 over X. Any questions on that? So I'm going to erase the red incorrect work and say, okay, we have our angle. We have our opposite side. We need our adjacent side. So tangent is the choice. So tangent of 60 degrees is equal to opposite 20 divided by adjacent X. And this is a situation that we haven't encountered yet. The last two times we've been solving these things, the variables have been in the numerator. That's not the end of the world, though. Remember, tangent of 60 degrees is just a number. So you can treat it like a fraction, and you can cross multiply. Or you could multiply both sides by X and then divide by tangent 60. However you want to do it. I'm going to do cross multiplication and get that X times tangent of 60 degrees is equal to 20. Yes.
If there's three angles, why is one angle? Wouldn't they all be 30?
So this can you ask that question one more time? Just like one more time. I need to hear it again.
Okay, so you said the green angle is 60, right?
Mm-hmm.
Because it's a 90 degree.
The full thing.
Yes. Wouldn't it be 30 per side?
So in order for this thing to add up to 90 here, we need these, like, so these two angles have to completely add up to 90. So one of them is 30, the other one has to be 60. Now there's some cool geometry stuff, by the way, going on here in the background. I can tell you immediately, since these two lines are parallel, that this angle measurement is 30 degrees as well. Don't write that down. It's not necessary. That's some geometry that we don't have to worry about. But there's a very, very cool geometry fact going on in the background. But that is another way to do it. You can find out that angle is 30, and then you could set up. So you could figure out for a multitude of reasons, this angle is 30 degrees because 90 plus 60 plus 30 is 180, and every triangle has 180 degrees. That's one way to do it. And then you could set this up and do tangent of 30 degrees is equal to x over 20. Then you don't even have to worry about this, but that's being more, that's assuming that we're being very, very clever on a time crunch when I can't guarantee that we'll see that, right? Maybe we're trying to think of it and then somebody sneezes in the middle of the exam and then we lose our place. And we don't want to, like, we just forget to be clever. It's okay. But anyways, so this one, x times tangent of 60 degrees is equal to 20. Remember, tangent of 60 degrees is just a number. Just a number. So we can, since x is being multiplied by tangent of 60 degrees, to undo that multiplication, we have to divide. Tangent of 60 degrees. And that cancels it on the left. So you get x is equal to 20 divided by tangent of 60, which is approximately, it didn't say where to approximate to, so let's just do 2 decimal places, but 20 divided by tangent of 60 degrees should give you 11.55. And it's going to be feet. And once again, if you don't like dealing with that, you can always write the approximation of tangent to keep it as a number. Any questions on that? Okay. So we've got 18 minutes left. I want to do a little bit on 1.5, and then we'll spend about like 5 to 10 minutes on let's see here. My notes on that. I think I can finish that all tomorrow. Right, I could do that. Yeah, we could do that. So we'll just do a little bit of review on unit conversions, just because I know there are a couple problems that threw some people for a loop. So let's go ahead and do those. So extra practice on dimensional analysis. Okay. All right. Let's make up an example. I'll do one that's kind of similar to something on the homework, and then I'll do one that's also similar to it. That is slightly different. So Geno Smith ran at 21 miles per hour during the Broncos game. For 10 seconds. How many feet did he travel? In case you don't know, Geno Smith is the quarterback for the Seahawks, which you guys should all know because we're all Seahawks fans here. Good job. Good. But very, very similar to one of the ones that you saw in your notes. It was like some person is running at this speed for this amount of seconds. How many feet did they run? Or how many yards or something like that. It doesn't really matter. So with this one, 21 miles per hour, that is a unit fraction. That is comparing two different quantities. It's saying that Geno is running at 21 miles for every 1 hour. If you were to continue on that speed. Apparently it was like one of the highest speeds of any quarterback in the NFL. So that's pretty cool. But anyways. The reason why I mentioned that is that the 21 miles per hour should be one of the unit fractions that we use. So we should use the 10 seconds to start this problem off. It's not wrong to do that. It's just you have to be a little bit clever if you decide to start with 21 miles per hour. You have to kind of finagle it a little bit. But anyway, so you start with 10 seconds. And remember that you don't have to be perfect as you go along. You don't have to cancel each unit as you go along. That's not required. You could just start off with what you know. You know that you're going to have 21 miles for every 1 hour, which is what I would start off with, 21 miles for every 1 hour. And so first off, I see that nothing's canceling. But I do see that I have a time measurement in the numerator and a time measurement in the denominator. So if I were to be able to convert those hours to seconds, that would be a good thing. So that's what I'm going to do first. So 1 hour is 60 minutes. That would cancel the hours. Also, let's try and keep in mind what our end goal is. Our end goal is to get a distance measurement. Yes.
Would you also cancel out the minutes as well, or?
Yes, we're going to need to cancel out the minutes. Careful though. Are you saying canceling out these?
Yeah.
So one of them is miles and one of them is minutes. So
Okay.
yeah, one of the bad situations, MI for mile, MIN for min. And that'll be but we do need to definitely cancel those minutes, and we'll convert 1 minute to 60 seconds. And then we'll see the minutes cancel and also the seconds cancel. So we've gotten rid of our time measurement. All we have left is miles. That's not what the question's asking. It's asking for a feet measurement. Any questions so far? The key thing is to remember that multiplication is commutative. 2 times 3 is the same thing as 3 times 2. You can change them how you want. And so even if you don't have the unit fraction that's going to perfectly cancel things right off the bat, that's okay. That's not like, you can jumble it however you want. It doesn't have to be perfect, as long as you're canceling units diagonally or vertically, you're good. But the problem is that we don't want miles, we want feet. But good news is there is a direct correlation between feet and miles. There are, for every 1 mile, there are 5,280 feet. And then the miles would cancel. And if we're looking at all the units are canceled except for feet, which is exactly what we want. So now we just need to use our calculator. It'll be 10 in the numerator. That's going to be 10 times 21 times 5,280 divided by 60 times 60. Remember, I'm not writing any of the ones because multiplying by 1 doesn't do anything. So in my numerator, 10 times 21 times 5,280 divided by my denominator, 60 times 60. And I get 308 feet. So that is a full football field return, actually. He didn't actually run for 10 seconds. It was probably more like 3 seconds, but if you ever watch, if you're a big fan of football or whatever, 3 seconds can feel like an eternity. So he didn't actually run 308 feet, but assume for this problem. Any questions on that? All right. One more example. A drug needs to be administered at a rate of 0.5 milliliters per minute. If the patient needs 8 fluid ounces, how long will this take? So we know the rate at which it needs to be administered to this to the patient. Any more than that, and the patient will let's just assume enter cardiac arrest. So we can't go higher than that. Let's make it severe circumstances. But after 8 fluid ounces, they should be cured completely. So if this is a problem on an exam, so I don't know this off the top of my head, so that's why I'm going to use my Siri. How many milliliters are in 1 fluid ounce? So it would say on your exam, note 1 FLOZ is equal to 29.57 ml. So on an exam, either you'd have it on the problem itself, or there would be a chart on the last page on your scratch paper page that tells you the exact unit conversion. So you don't have to have any unit conversions memorized. Don't worry about that. Any of them that are needed will be provided. And some of them might not be, that they might be quote unquote common knowledge. But if you forget, that's fine. Like if you don't remember how many weeks there are in a year, that's okay. Just ask. If you forget how many seconds there are in a minute, just ask. It's fine. But anyways, this one. 0.5, and how long in hours? Let's say how long in hours. Sorry, I should have mentioned that. All right. Solution. What should we start off with? Actually, so I would say that the answer should be the answer to my question should be that you should start with the 8 fluid ounces. However, what if you don't do that? What if you start with the milliliters per minute? What's going to happen? Let's see. 0.5 milliliters per minute for 1 minute. All right. So I look at this and I say, well, I don't need milliliters. I need fluid ounces. So I need to convert the fluid ounces to the milliliters to fluid ounces. And I know that there are 29.57 milliliters for every 1 FLOZ. That cancels the milliliters. Then I know, so this is not going to get me the right answer. How do I know that? So one of the things that you might have noticed when we've been doing these problems is basically whatever degree, like a specific quantity measurement, whether it for example, volume, so like milliliters or centimeters cubed or whatever it may be, it always stays in the same spot in the problem. So if you notice in this previous one, the time measurement, well, no, not necessarily. Never mind. Let's see what happens. Let's see what happens. I don't know where this is going to go, so let's have some fun. So we've got rid of the fluid ounce. We got rid of the milliliters. We know that the patient needs 8 fluid ounces. So what we can write is we can write a unit fraction. We can say 8 fluid ounces for every 1 patient. You could write it as that, or 1 treatment. 8 fluid ounces for every 1 treatment. In fact, you can even write just 8 fluid ounces and have no denominator. It's not really required. But that, oh, wait. It needs to be flipped. It needs to be flipped. And so that will cancel the fluid ounces. And we've got treatments per minute. So whenever I keep canceling the minutes, you'll notice that I keep getting them like the degree, like the measurement of time always in the denominator. So just like, let's just carry this out and you'll see what's going to happen. I wanted to know how many hours. So when I do this, I'll convert the 60 minutes to 1 hour. And the 60 minutes will cancel. And then I've got treatments per hour. But I just want hours in the treatment. So what I actually needed to do is I needed to start with 1 minute per 0.5 milliliters. I needed to flip the first unit fraction on its head. So I didn't get it right. I needed to start from scratch. One thing you could do, and it will fix it completely, is to just take the final answer and divide by, like put 1 divided by your answer. That'll fix it. But let's just say it's okay. We can cross that out. It didn't work. See your plan through until the very end and then readjust. That didn't work out. So let's try and start with the 6 fluid ounces or the 8 fluid ounces. I'm going to use the fact that 1 fluid ounce is 29.57 milliliters to cancel out the fluid ounces. That cancels the fluid ounces. And that will tell me exactly how many milliliters need to be administered. Then I know that I have a rate of 0.5 milliliters per minute. So that's 0.5 milliliters for every 1 minute. I need the milliliters in the denominator because that's the way I will cancel them. If I put the milliliters up top, then I get milliliters squared, and that's not what I want. I want to cancel the milliliters. I don't want a volume measurement. Last thing, though, is I don't want minutes. I want hours, and we know that there are 60 minutes in 1 hour, thereby canceling the minutes. And now we've just got hours. If we look at everything, we just got hours. So yes, I did it wrong from the first go. That's important to see. Sometimes we don't get it right on the first go. Happens so often, you'd be surprised. Even for me, I mess up things and then I'm like, okay, I need to readjust. I don't take it as a sign that I'm bad at math. And you shouldn't either. Just because you get something wrong when you start off with, that doesn't mean squat. So this one will be 8 times 29.57 times 1 times 1, which is unnecessary, and then 0.5 times 60 in the denominator. You get 7.89 hours, approximately. Any questions on that? Okay, we'll start up 1.5 next time and finish it hypothetically all in one go. If you have any questions about that, feel free to ask. And if your calculator is still in radians and you need it changed to degrees, just come up to the front and I will happily change it. Otherwise, have a great day and I'll see you guys on Wednesday.